Okay, so here's the lecture for living in a flowing environment. Just kind of wanted to spend some time thinking about, okay, so you're an organism that lives in a stream. What does that mean and how do organisms cope with that? So, first off, well, living in a flowing environment, really we're talking about moving water. And there's some good things and some bad things about living in that moving water. So the first thing, it transports food, right? So what we have here is this is a net-spitting caddisfly. It's rather than having like a little dirt burrito, like we called it, right? Rather than having a little case, they have a net. And so the little insect lives way back here, and then it comes out, and this net is inflated by the water movement, and organic matter comes in here, gets trapped in the net, and then the little caddisfly can eat whatever it wants from what caught on the net. And it doesn't need to then go out and search for food. It just can find it on its own. The water basically brings the food to it, right? So these are little blackfly larvae that are on the top of these rocks in really high flow areas, and then they have little fans that they stick up at the top of their heads to gain or to filter out. Also, organisms are not, they don't need, so food comes to them, but then they don't need to worry about bringing water and putting it over their gills because the water is actually flowing over their gills. So think about a shark, right? A shark needs to continuously swim to keep water coming into their mouth and going out their gills. I realize there's sharks that can stop for a while and do things, but most sharks, need to keep swimming. So I'll put a link to this video in the description, but it's a little stonefly that is doing little push-ups, and that to put water across its gills, and it doesn't need to do that most of the time in a flowing water system. Also, think if you're this mussel here, as you're basically pooping, the water just takes that poop away from you, and you don't need to worry about an accumulation of waste around your specific home. But there's also some problems living in a flowing environment, right? Getting dislodged from where you are. If you're not a strong swimmer, that's a big problem. So we see a lot of adaptations to living in a flowing environment. This is a sculpin, and it has these cool fins that are along the side of its body that then are kind of angled. And what it does is as the water flows this way, it hits these and the water gets pushed up, thereby pushing the fish down into the sediment. So sculpins don't actually have swim bladders because they're completely abenthic fish that kind of just swim right along the bottom of the water and want to stay down as low as possible. So this is a heptageniid mayfly that is real streamlined, and you can see how that is as the water just kind of can flow right over the top and keep that bug squished to the sediments, and it can go around with essentially being within this boundary layer, right? Because as you go from up in the water down closer to the sediments, you hit this boundary layer of water that isn't moving as quickly and is eventually going to zero. So if you have a small enough insect, it can actually live within this boundary layer, and while it might be even like on the top of a rock, as long as it's within that boundary layer and it can essentially become part of the sediments, then it will live in an environment that is really not that harsh as far as water flow, and you won't have as many problems with dislodging. So we'll talk about functional feeding groups later on, but in organisms that filter stuff, so filter feeders, they're going to be in areas where that correlate with shear stress. Shear stress is basically just how much water flow is going on in a specific area, and they're going to be so a mussel or something wants to be where there's a lot of flow, because the more flow equals the more food that's brought to you. But things that are collecting, so a lot of midges and a lot of other types of insects crayfish will be in areas that you don't want a bunch of water flow, because they're depending on water coming, slowing down, and all those organic materials settling out onto the sediments that they can find. And if you're in an area that has a bunch of flow, all the organic matter just gets washed downstream. So what we see is body shape is really important in this. Take a look at these fishes. Which ones do you think live in streams? Well, agar, pike. Now, certainly pike also live in lakes, yes. So do walleye. But what you see is that's for different reasons. Definitely in streams, pretty much everything is long and skinny. Because remember, at large size, that streamlining is super important. So we find fish like this, fish like this. If you want to swim fast, so the pike and the walleye here are fish that do need to swim fast, but that's because they're predators. And you just don't really find that many fish that are really deep body, especially these oceanic types here, the sunfish and the moonfish. These would be horribly adapted to being in a stream. You just don't find real deep-bodied fish. You only find real tube-shaped fusiform. That means tube-shaped fish in streams generally. So, but even though maybe you have this gar that is super streamlined, right? But where is it going to be? So fly fishermen really know where this idea of, think about if you're going to go try to catch a trout, which are relatively streamlined fish, right? Are you going to cast way out into the middle of this pool, or are you going to try to cast right behind this rock or right behind this rock, right? And the answer is, most people know, cast behind the rock. And that's because, think about it from an energetics perspective. When you're in the middle of the stream, you have a ton of flow coming at you. So what you can see then is, you can see that these are all these little mayflies that you're going to want to eat, right? This fish here might be able to see a whole lot of mayflies and eat all these 4 mayflies. So it gains some energy, but most of that energy is lost swimming against this flow. So what about this scenario? Well, this fish here does not see as many mayflies, but since it only has to work against a little bit of flow, it doesn't have as much swimming energy. So even though it might be eating less, it gets a higher energy gain. So when we're thinking about flow, fish are oftentimes trying to avoid flow as much as possible. But it's not just flow, it's all organisms want to avoid flow. And so they find these flow refuges at different places depending on how big the organism is. So if you have just a tiny little mayfly that's only 5 millimeters long, right, at the surface, so if we zoom in on this rock, you might have tiny little crevices in that rock where tiny little organisms are just fine and are completely, this water might be flowing very quickly over the top of this rock, but they're fine in these little crevices. Slightly bigger scale, think about a little darter or a tiny little crayfish or something, can live in between these little rocks and be just fine and not exposed to a ton of flow. Get a little bit bigger, behind boulders, behind woody debris dams, behind sandbars, or in these big backwater areas. So there's different scales of flow refuges depending on how mobile the organism is and what size that organism is. But what we generally see is in streams, most everything tries to avoid flow in one way or another. And those flow refuges, though, can become a really big problem if there's a sedimentation event or a siltation event. So what we see is any substrate of the river is really determined by how fast the water is flowing and what the bedrock is made out of. And what we see is the more heterogeneous the substrate is. So take this river here where you've got big rocks, tiny little rocks, and then there's sand particles, all sorts of stuff in here. So you have little interstitial spaces of a variety of different sizes, meaning you get all sorts of different organisms that can live there. So you'd have the highest diversity. But if you if there's a farm field made here, all these trees are cut down, you put a farm field right here, what you're left with then is a bunch of sediment going into the stream that the stream might start out like this with all these little interstitial spaces, but as it gets filled in with sediment, all those spaces go away and you're left with just, a dirt bottom rather than all these little crevices that can house lots of different organisms. So what we generally see is the bigger spaces, the more heterogeneous those spaces are, the more organisms you eventually have. Small sediments are really considered poor habitats for a variety of reasons. So if you think about a sandbed river, as the river flows and floods, all this sand gets mobilized, and it's like, if you're a tiny little organism, you might get hit by those sand grains coming down, and it can really just crush you. What we see is in this sand, there's not really that much ability to trap anything. So there might be just a little bit of organic material at the top, but it doesn't trap any detritus, so there's not that much food sources. As soon as you go into that sediment, then you run out of oxygen very, very quickly, right? Because even just a millimeter under here, there's no light. So, and because the sediments are so packed in together, there's not that much water infiltration into those sediments. So you don't get any photosynthesis, you don't get water flow in here. So it's relatively low oxygen. And then because this sand is the most unstable, remember it requires the least amount of flow to move those sediments, you get whole habitats rearranging on hourly, daily basis. That it makes it really hard for those organisms to then deal with that. So what about other types of substrates, right? So there's plenty of plants in streams and plenty of wood in streams. The thing is, we oftentimes think of plants as this really good food source, but when we're thinking about aquatic organisms, you should really think of them as substrate and not food. It's really weird, but in aquatic systems, pretty much nothing eats the plants. Now, when I mean plants, I don't mean algae and periphyton. What I'm really referring to is the macrophytes, the big plants that you see. So, whether the grasses, lily pads, submerged plants underneath in the stream, nothing really eats them. Nothing really eats also wood. Even on land, you don't see that much wood being eaten, but in the water, it's even less, right? There are no aquatic termites. Cool, interesting story. There's this old man of the lake. This is Crater Lake. It's a really oligotrophic lake in Oregon. And there's this log that they've geotagged. There's like a GPS tag on it, and it's been floating around the lake since at least 1896, right? So I think that goes to show that there's definitely nothing eating that wood, at least in that lake. And what we see, that also translates to streams. Really, it's, as wood is breaking down, it's really mostly the physical forces of that water making that wood softer and then breaking pieces off. So let's move into then invertebrate drift. So if you look at any stream, there'll be bugs floating down the stream in the water column. But there's some weird patterns to this. Generally what we see is that during the day, there's not that much drift, but drift really peaks at night. And what we see is drift is most common in smaller streams, but you can also find it in bigger rivers too. Now there's a variety of reasons that an organism might want to go into the drift. So this is a drift net where they're trying to figure out, doing some experiment, figure out what's flowing down the stream. So why would an organism want to go into the water column? Well, let's say you run out of food. You're a little tiny bug, run out of food in your area. Rather than crawling and swimming to someplace, just go up into the water column for a little bit, takes you to a new spot. Hopefully you'll get to a new spot. So could improve your foraging. Well, what if a fish is coming nearby and you need to swim away? Well, oftentimes you're probably not going to beat the fish as far as swimming speed. So get off the sediments and wash downstream. But then organisms also just get accidentally dislodged, right? We're talking about insects here. They're not super smart, so they might just accidentally fall off their little rock or their little piece of wood and get moved downstream. And what we see is that all of these things, though, happen more often at night. Because there's fish that are visual predators, anytime that you're up in the water column, you're exposing yourself to a lot of predation. So when we see streams that don't have drift feeding fish, you don't really see this pattern. But all of these things happen more often at nighttime, right? If you're under the rock in the stream, under the rock during the daytime, you come out at nighttime to eat the periphyton maybe on top of that rock. Well, that's the time where you might run out of food in your area, so you have to travel. You might get accidentally dislodged. And when you're on the top of the rock, it's a lot easier to get dislodged rather than underneath the rock. So all of this is going to make for nighttime being more drift. Excuse me. So nighttime we have higher drift in the streams compared to the daytime. Another topic I want to talk about is river plankton, potamoplankton. And the question is, are river plankton actually natural? Because there's a lot of things that got going against them, right? So think about, the Mississippi River, right? You're a tiny little plankton that is in the river up here in northern Minnesota. Well, real quickly you get washed downstream. And so the question is that like a natural situation, or is it just they were in a lake, let's say this lake right here, that then got into the water and then washed downstream? So are all the phytoplankton, the free-floating plankton that we find in a river, just due to being in a lake that gets washed in, or is there some other reason? There's this one-way transport, right? How do you get potamoplankton up in small streams if it's continuously being flushed downstream? And because of the helical flow, then you often get the phytoplankton itself being in the aphotic zone. So that's another thing that got going against them. And then rivers are also, remember, geologically really old, right? Millions of years old, where the lakes themselves are not very old. So are river plankton natural, or are they natural to the stream, or are they just they make do with the river even though they're from the lake. So what do we see? Well, lakes and rivers have similar species of plankton, but they differ in relative abundances. Okay, so rivers have more diatoms and cyanobacteria, do much better than green algae do in lakes, right? So we actually do think pentamoplankton are natural, endemic, or native to rivers. And that's because there's a variety of ways in which, yes, there is this one-way transport, but what we see is there's plenty of airborne recruitment, right? Algae are put up into the air and blown around all the time, so they might get blown into the headwater streams that way. Slackwater areas, so these, backwater areas that we find in rivers are a huge source of plankton that then feed into the river, and you can have really, really high production in these areas. Also, just in the river itself will have high production because there's generally more nutrients available to river systems than in lakes. But these slackwater systems, we got to think of, even just along the shoreline, there's lots of tiny little slackwater areas where water is moving more slowly and does a fine job of producing a flow refuge for those riverine plankton. All right, that's it for the living in a flowing environment. Check back later for more videos.